anyway, thank you for coming. I'm James Munro, and I'm going to talk about why a hedge fund built its own database technology. Originally, the title was database, and I realized that actually means the data, right? So database technology. There is a disclaimer, which the compliance team helpfully filled the white space with, because I do work for an asset manager, and so opinions are my own, and none of this is investment advice. So I run ArcticDB at Man Group. Man Group is the asset manager. And I'll just introduce myself a little bit. Okay. So I was a physicist originally. Spent some time doing plasma physics, electron molecule scattering, things like this. And that ended up being useful to do simulations of plasmas for semiconductor processing. This is marginally relevant to a later bit in the talk. But eventually, I gave that up, joined Man HL, which is a very systematic, quantitative hedge fund manager, mostly hedge fund manager. And I worked as a quant dev on a bunch of their asset classes, teams, strategies, and portfolio management and things. Became manager in 2016, then CTO in 2018. And then really that's where I feel like a lot of what I'm going to talk about starts to come in, where I'm focusing on particular things for Man HL. And I did that for 5 years before becoming head of ArcticDB. So I actually sort of moved from being like the biggest user of ArcticDB, running the team that was using ArcticDB, and like demanding features left, right, and center, to being like the owner of it, which is kind of an interesting twist. So I'm going to give some context, to sort of sketch out the story, and then talk about the real whys of building your own database technology. So Man Group is a large alternative asset manager. Alternative means, not the usual massive markets, but alternative investments designed to give kind of uncorrelated returns. So we're quite large for that. So over $160 billion of assets under management. And we've been doing that for a while, 35 years. Actually, Man's much older. It's named after someone called James Mann, who founded it in 1783. So it's a very old company. And has been doing like brokerage and merchanting and stuff for most of its history. But for the last 35 years, it's been predominantly asset management. Lots of clients. Mostly sophisticated clients. In fact, you have to legally be a sophisticated client for most of the stuff. And the things like pension funds who are looking for like other sources of alpha for the people with those pensions. And this is like a really broad range of investment strategies. So things like macro funds, trend following funds, multi-strategy things, like discretionary things, credit, loans, all sorts of things, real assets. So there's a whole like diversity of things going on. So anything in alternative asset management has kind of been something that Man Group's interested in. And all of that has now kind of been supported by this single technology and operating platform. And that's where the story starts to get interesting for us, I think. So because of the size, there's a scale challenge immediately. So we trade an awfully large amount for an asset manager, so 6 trillion or more a year. So it depends on the vol of the markets, the kind of level of risk we're taking. But that kind of scale. And how do you get from 160 odd billion to 6 trillion? Like that seems like quite a lot. So quite a lot of a jump. Well, actually, several fold comes from leverage. So if you're running hedge funds, you're normally running leverage. So that's the first factor. The other kind of several fold from, say, 1 trillion to 6 or 7 trillion is actually because you're an active asset manager. So you're using data and information on the markets to decide whether you should be long, short, which markets you should hold. And it's that you're using to trade. And that means you have to be coming in and out of positions. And you're doing that several times a year on average. So that's kind of where that scale comes from. And then we're looking for like a whole diverse range of ways to sort of find alpha for our clients. And that's where you need to trade lots of markets. So anything liquid we will trade, basically. And then we've got all these different customers with different problems. And so we're trying to design it for all of them as well. So there's this real alpha at scale challenge. And then trading. You've got to do this cheaply. You've got to do it efficiently. It's a real drag on this kind of activity if you're not getting into the markets like really, really, really cheaply. So another little bit of context is about the story for Arctic itself, so just at a high level. So this is something we actually started back in about 2011 when we were looking at Python as a platform as well, and we were looking for data solutions that would work for us for that. I'll come back to that story a bit. But we built a first version of Arctic, and I'm gonna try and explain the why for both simultaneously, so this won't come up that much again. But we made a first version of this Arctic database actually purely in Python, and it was backed by Munro at the time, which is kind of like a fast document storage database. And we did that, and then we actually open sourced that in 2015, which got reasonably good usage by our peers in the financial industry. And that was kind of like first half of the story. But really, we started to hit limits with that. So Mongo became a bit of a scaling obstacle for us. We were running hundreds of Mongo servers. And apparently, we had like the second largest Mongo installation for a while. And we needed another way to level up on the performance as well. So we rewrote the core in C++. We actually got rid of the separate database layer completely. And now it connects just to storage. And so that's one of the stories I'm going to talk about. But this was a way, therefore, that we could, by changing our way we do storage, so connecting directly to object stores like S3, we could get better performance and better scale. And then also by changing the runtime, C++ instead of Python, we could get better performance, what we're doing there as well. So that was a way to double, like, many times our performance level on our scale. And that now is used like almost for everything at Man Group in the front office at least, so for all our market data and all the data we use to predict markets or risk or whatever we're doing or costs. And for all of the AUM that Man Group trades. And it's also used across finance now by banks, other asset managers, data providers. So that's, let's get into the why. So that's like just context really. So why build a database? So at one level, it sounds crazy. There's thousands of databases out there, and they've all already been built by people who want to make a successful database for some reason. So is it really the case that none of them fit what you're trying to do? That's like a core of the question. And so at some level, this sounds a bit crazy, right? And it reminded me of this quote. The distance between insanity and genius is measured only by success. Which after a bit of Googling, I found out was made by someone called Bruce Furstein, who apparently wrote some of the James Bond stories, an American author. And this is the DALL-E interpretation of that. I love that we can all do these DALL-E images in presentations now. I'm worried that it will suddenly become unfashionable within like 6 months. But anyway, I think we can still get away with it. So this is the interpretation of that. You've got the slightly crazy person on the left and the maybe more genius-y person on the right. And then that was the way around I had it in my head anyway. And a younger-looking Bruce Furstein in the middle. And he's measuring his head size for some reason. Anyway, I kind of got it. And then you get these weird things like the arm coming in from the left on the table. I don't really understand. But is it crazy? So I don't think it really is, because for one thing, there's some level of specialism here. We're dealing with a lot of high-frequency data, and I'm going to talk about shapes and sizes of data. Two, and that's a normal thing for people to go and solve with specialist tools. There are proprietary databases you can buy for tick data, but you'll find that most, at least tier 1 banks, have built their own proprietary database solutions for tick data for the kind of the similar reasons that I'm going to talk about. So there's a specialism story there. But actually, we built something that's quite general. And I think another part of that is actually, like most of those 1,000 databases out there, I'm guessing it's 1,000, it could be 10,000, but most of those 1,000 databases out there already have been built for a purpose. So very few databases are kind of like built in a vacuum and then address a purpose. So actually, I think you should really consider it normal that when there's a breeding ground for some sort of innovation, that someone comes up with something that's a little bit different. So getting into the why, I wanted to try and connect the dots from what Man Group's trying to achieve with this kind of alpha at scale story back to the technology pressure for doing something like ArcticDB. And this is quite a nice way to explain it, I think. And this is an economic article from American Economic Review in 2020, where they were looking at research productivity. So you might think that like maybe low latency trading systems are the real challenge of running a systematic quant hedge fund. Turns out not really. I mean, we're not a high frequency trader. That's one element of it where that would be more of a pressure. But actually, and although that does matter, like the performance of that does matter, and the technology you need to solve like high frequency trading and really good execution does matter, actually you'll find that a lot of the time you're competing on this research productivity for the trade ideas themselves and how you manage risk and optimize portfolios rather than the low latency aspects of it. I'll explain that a bit more. But what that means is, therefore, that you're really trying to, one step back from generating the alpha itself is actually the research to generate the alpha on the data. And so it's the research productivity for your quant team that you're focused on for those ideas, for that kind of portfolio construction. And so this chart is of that for Moore's law. So this felt familiar for me because I've been working on semiconductor processing in the sort of mid-2000s there. So I'm a little part of that green line. And what it shows is that for Moore's law, in that sector at least, we know the semiconductor density's doubled every couple of years. Somehow that's 35% compound growth rate according to the economics. But I didn't quite get that. But that's been an exponential growth rate, right, for the computing industry. And it's been a massive revolution, right? The IT revolution, the technology revolution. But the cost of that, the cost of doing that research has been going up steadily. And I was definitely acutely aware of that because of the level of detail for simulating those plasmas, etching those semiconductors that I was doing. I mean, it was atomic level simulation back in the mid-2000s. Meant that, and that was very much at the tail end of the concerns. Like the number of people that just to eke out the smaller and smaller feature sizes on these things was just getting huge. And that works when your payoff is exponential. It doesn't work in every market. But if that was one person in 1971, it's now like 18 people in 2014. It's probably a lot more now. So research productivity is a key challenge in that sector. And the paper's conclusion is it's a key challenge across sectors. And some of those sectors don't have those exponential payoffs. It's a key challenge in quant as well for markets. For one thing, you've got more data coming in. Another thing is you've got competition. And you've got market efficiency going up. So these edges become harder and harder to find. So this research productivity ends up being your biggest challenge. Data's going up. No need to explain that. In asset management, in financing generally, though, it's been a slightly more nuanced story. So high-frequency data, low-latency market data ticks, right? That frequency of that's been going up. You can collect trillions of rows per day if you want. Billions of rows per day is typical for asset managers like ours. But also, there's been another part to the story, which is all this other data starting to get used to predict markets and risk. And generally, we refer to that as like alt data or alternative data. So that's all the data that consumers are generating and people are generating, which is all sorts of different types, right? It could be weather data, images, could be data on how green you are, all of this stuff. Anyway, this stuff's been growing. So there's a sort of dual-sided story here, where it's just the volume of this data has been growing. But this plot here is by a data catalog company. They basically go and index data sets for people to try and connect you to the valuable data you might need, called Eagle Alpha. And they've got this nice plots of all the data in their catalog, all the data sets in their catalog over time. So actually, it's also a diversity of data challenge for a place like us, where you're dealing with all sorts of different data types, and you just really need to be able to get through that as a process really quickly as well. So you need agility with data, not just the ability to handle it performantly. And then another sort of part is just to I wanted to place this story in time as well, because think back, in 2011 when I joined Man Group, they were just beginning a move to Python. Everyone uses Python for data science now, right? Or anyone who's choosing at this point. People might be on other languages at the moment, but anyone who's choosing is choosing Python for data science, and that's what you get taught at school and everything. That wasn't really the case in 2011. I think that if you're in a quant hedge fund in 2011, you're looking at things like R, other languages like R, or things like MATLAB, sometimes C++ if you're doing lots of data. These were the kind of typical choices. These were the skills that people had in the building. And Python wasn't the obvious choice for data science at that point. And also, you were presented with the challenge of wanting something you could use in prod. And it wasn't really a choice for that at the time either. But obviously, lots of people have been choosing Python since then. You can see that. This is the Stack Overflow language popularity chart. And you can see lots of people chose Python, and it became very popular on Stack Overflow, and obviously very popular globally. Back then, also, Python 2 was like normal. Python 3 was out, but it was like hard, still a pain, right? TensorFlow didn't exist. PyTorch didn't exist. Lots of tools weren't that popular yet. Pandas really got popular kind of mid-teens, maybe. It was open sourced originally in 2008. So this was still kind of a pushy choice. You're going to move everything into Python. You're going to do everything, all your data science there. And so we spent time supporting that community, particularly PyData in London, and working on our tooling on top of what was available, including ArcticDB. And I want to sort of explain another part of the conceptual journey, which is that, right, even if you're an individual and you're managing your investment portfolio, this is the process you follow. And even if you're like a very sophisticated asset manager, this is the process you follow, whether you like it or not. So you're bringing data in. As an individual, I might just look at my phone for a price of something. I might be bringing in billions of market data ticks. You're trying to get on board that data. You're coming up with some decision, some idea about what to trade. And then you need to decide how to trade it, right? This portfolio construction. Maybe it's not the only position you hold. Maybe a simple example is you want to hold American stocks, but maybe you don't want to be exposed to the dollar. So you might need to hedge something. But in the complicated case, you've got to decide on your weighting to all the assets you might hold. And then you want to trade it cheaply. So that might affect the instrument you trade, but also how you trade. This is whether you're an individual or whether you're a global corporation, this is the process you follow. So, but I think the other part of the story is that, this just really gets complicated extremely quickly. So you're talking about, I mentioned the thousands of data sets that Eagle Alpha had indexed there. The variety of data as well. You might be looking at company reports, so like documents. You've got tick data. You might be looking at like consumer transactions. You might be looking at like environmental, social things. You're also doing all sorts of statistical methods. It's not like you're choosing one machine learning algorithm that's on trend. You're doing like basic statistical and science. You might be doing deep learning. You might be using ChatGPT. So you're almost using every method under the sun that you can get your hands on. So you need the kind of like the tools that let you do that. You need to be doing all sorts of portfolio construction. I mentioned that we've got lots of solutions. You need to do risk, and you need to also do the high frequency end of execution. And you need to do that well. So you've just got this really like diverse set of problems and almost like teams like devoted to all of them. So there are hundreds of quants within Man Group, for instance, and they all want to be solving different problems. If you're all solving the same problem, you're probably doing something wrong. So, okay, now we're getting into the nuts of it. I think the detail of it. So if you're a systematic trader, which means that you designed an algorithm that's going to do the work for you, right? You're not choosing stocks yourself. You're designing the algorithm, and you're probably very automated, so from data through to execution. Then invariably, and I think this is like the architecture for the ages, called like the Lambda architecture, which many of you will be aware of. You invariably invent this Lambda architecture where you have streaming data pipeline and a batch data pipeline. And so streaming data, it's all about the high frequency stuff, and you're bringing in tick data, you're saving it into tables or data frames. You're also going to be downsampling it into bars, typically 1 minute bars, could be lower frequency, higher frequency, and doing analytics on it for later use. But also, you don't want to do the kind of work that requires and connecting to non-streaming APIs for everything else. You've got like a batch workflow. So that's the other side of the Lambda architecture, where you're bringing in like either fundamental or alternative data for all the things that you care about. You're putting that into data frames or tables. You need to catalog that because there's thousands of things. And we've got this internal data lake architecture we call Codex. And then the goal is to bring this stuff into your model, your strategy, where your algorithm is going to execute, and it's going to use this. It's going to be able to do back tests to tell you how this thing evolves over time. It's going to do portfolio risk and trade optimization. And that's like where the science is focused on building that algorithm. And then you'll send that instruction out to trading, the eventual like thing, the decision, if you like. And that could happen in a variety of ways, but then you're going to need to do analytics on that. You're going to need to do analytics on all of this to see what's going on. And so you're bringing this stuff into tables. What's happened at Man Group and actually at many alternative asset managers is the table has become the data frame, right? The data frame's become the unit of moving data around, almost like a document, in that you care about the unit as a whole. You're reading and writing new ones every day. And so you're just shuffling an awful amount of data around, and you're doing analytics on all of it every day. And so that's a key story, that your unit of operation is the whole data frame. And then from the technology side, back in 2011, but this is still something we care about, we were thinking about how to get past the server bottlenecks that all of this kind of stuff causes. And we tried a number of proprietary databases and open source databases at the time. And we found all of that required often just creating like hundreds of these servers. And I talked about the Mongo story a bit, but the reality is that a single user can generate enough load with some of these like data science models to swamp your entire system, to swamp potentially dozens of servers, which is like the inverse of like a relationship you might have with a website, right, where you've got thousands, potentially millions of users for a single server. And that's a huge cost and a huge operating like burden as well, just the cognitive load and the work requires to maintain that, even in kind of modern serverless setups. And then also we were moving to Python, and that was a decision we had made, and we wanted to make a really trivial API for people. We wanted to just make it as easy as possible to work with this data and data frames as a unit. And something that was a bit like, almost like OneDrive now, where you can just share data trivially and work on it like that. But also was a high-performance time series database. So this kind of like not having an obscure idiosyncratic tool for this, but simple Python API that let people work with data like this. So all of these things sort of coalescing drove us in this direction. And then, is there anything that could have still managed to not make us build our own database? And I'll explain a bit of that now. So with some of the real-world data challenges and my opinions on it. Time for a DALL-E picture. So shapes that are too wide, too long, or ragged. And I wasn't liking the images, so I added cubism on the end, try and get a cubist image. I'm not sure this is cubism, but it's got cubes in it. So here's someone struggling with real-world data. So a real example, bond data. I think it's an interesting example because people might not be so familiar with it, but bonds are actually a bigger market than equities, like multiple times, 3 times globally, as of when I pulled this data in, and actually a higher amount in the US because most bond trading is done in the US. So it's a huge market, actually, but it's a lot less liquid than equities. We all know about equity trading. It's credit, basically, and so it's much slower and harder to trade. It's OTC market. But this has been fertile ground for quant because because it's kind of less liquid but really big. It's something that's hard to do, it's something that's hard to get right, and so it's a really good thing to be on the front edge of. So the data behind this ends up being somewhat challenging as well. So I've got at the top like how you might think about like normalized data typically, and then I've got at the bottom one of the ways. In fact, we have many shapes for all the things we do, but one of the ways we actually work with this data. So at the top, this is Python, pandas data frame. And then I'm pulling out the bond data, and I've got dates on the left, so it's like a time series. I've also got IDs of the bonds. So those that you know, the QSIPs and ISINs are common IDs. And you've got things like price, but you've got lots of measures for the bonds, lots of fundamental data, things like duration. And this is like a normalized way of bringing in data. This is how you often get data. But it's not actually how you want to work with data. And that's one of the kind of steps I think you've got to take. So at the bottom, there's a pivot of that where you've got, you're just putting out price now, right? So one measure, you're just working with one measure because you want to do calculations on price. And if you do a calculation on price, it's not the same calculation you're going to do on volume. So you've got IDs along the top, and you've got times down the left still. And now you can do time series analytics. And if that's stored in a columnar fashion, then that's incredibly fast. But also, you've arranged your data naturally for doing cross-sectional analysis, because everything's a portfolio now, right? Trading one asset rarely makes sense. So you're really arranging yourself for the kind of work you want to do on this data. And this ends up being like 400,000 like historically tradable bonds from this data set, which is many gigabytes. So it's 5 rows because I pulled the tail out. But like it's a few thousand rows in total of like daily data. But it's many gigabytes of data. Wouldn't fit on this laptop, for instance, in RAM. So you also need the tools to deal with this. And you need something which is happy to have that many columns, which is not a typical SQL schema. And it's more like something you need to treat as a block. So this is really the story of the normalization trade-offs, and maybe personal opinion as well. But you know, generally people have been taught to design schemas on the left. And I'm not saying they're wrong, but I'm saying you need to think. So schemas on the left are typically like kind of normalized. And the reason you're doing that is because you're looking at the way the data is structured, and you realize not every timestamp exists. And you realize that sometimes assets like come and go. You know, Apple didn't exist forever, and many companies go bust. And measures change because your scheme, you know, the schema of your data often changes. So you've got to normalize it all because you think that's the right thing to do. And that's the kind of thing you sort of get taught to do at university if you do computer science. Luckily, I didn't do computer science. But actually, your users care about something else often. I don't want to be too generalistic. And so here I've given another case where it's not like assets IDs along the top, but it's like you've broken up your problem into assets. Because typically, maybe you've got an application where people are just pulling in individual assets. You don't actually want the performance cost of building the table on the left, but also the performance cost of scanning the whole table every time you want one asset out of it. So suddenly, you want the columnar storage on an asset, right? And two, your measures might change, or you might have something else. You might be doing calculations producing the columns. But you want that stuff aligned. You don't want that to be distributed across your large table. So actually, like, go to where the user is. Like, I wish I could like bump my fist on the table and explain. Like, go to where the user is as much as possible, and then do the normalization you think is appropriate for that. So that's like a real part of it, and has made us like design it for the flexibility of data frames that are the shapes the user want to be. So 2 aspects of that is just like, one, we can have big tables, but let's make sure those tables are columnar on the things that people want to read. And that could be billions of rows. It could be trillions of rows for tick data. Or it could just be decades of daily data. But also, users are going to want to do cross-sectional things. And so support, hundreds of thousands of columns. We have a user on ArcticDB doing 1 million columns. And so, make sure it works for that. But then, rather than rely on your normalization to deal with missing data, just accept the missing data. So let your data be ragged, and let your data be sparse in places, and to build a tool that's performant for that. So so you can see, if this is, again, just an example, because you're going to have many use cases, but if this is asset IDs on the top, then the idea is that some of these assets have gone away. Maybe they went bust, and new ones are coming along. Maybe if it's bonds, they've expired, and new bonds are being issued. Or maybe you're just missing data because a server went down. Right, so just build the tool that lets you work with that. because that's how the quants are going to work with it. And I think that's actually probably quite true of a lot of data science as well. So how do you go about solving for all this? So if you believe the why, okay, why build a database, a new one, then how do you go about solving for all this? So time for another Dali picture. Our mascot, the polar bear, is looking for a way through a complex architecture. And so my take on this is, and I'm sure I don't need to explain ACID to many people in the rooms, and this is where Ian's joke comes from, but my take on this is you can give up one of the ACID mostly. So we know atomicity is the idea that either something happens or it doesn't happen, like it fails completely or happens completely. Renaming a file on a file system is a common example of that. Consistency, all the versions are good versions. You don't see half-complete versions or things which break things you expect to be immutable. Durability, so there's copies of the data. You've got good uptime. So these things, yeah, you need these things. I 100%, you need these things. So the one that's missing on here is isolation. So if you want to give up anything for the sake of agility and performance, I think you can do a lot by giving up on some of the isolation. So this is like, e.g., isolation means that you're helping the user coordinate transactions, and they might be doing it from multiple places. So a very classic example of this is your shopping basket, right? So you've got stock, you're buying something online, that shop has stock of that thing, and it can't sell it twice, so it needs to check in order when it puts things into shopping baskets so it doesn't oversell it. In trading, this matters. I've got positions in something. I need to know that the last person who wants to change that table, i.e. me, if I want to change that table, saw that value, and no one else is operating based on that value until I've done my change. And so that's the serializability of individual users transacting on the database. So that, if you're moving to a world where you're actually doing analytics and data science, instead of trying to operate an order book in a trading system, then that's something you can easily give up, because you're actually asking the user, who's already got millions of these data frames, they're like documents to the user, right? Just to think about how they change that data frame rather than try and write to it from multiple places. So really the point here is that isolation needs coordination. And that can be a serious cost problem, maintenance problem because suddenly you need databases. Because you need a queue or locks, or you're limiting yourself to these obscure data types that kind of are eventually consistent. So, and by the way, you can do this without separate database servers. You could implement this on AWS S3, but it would be really, really slow and inefficient because you're really asking a lot of the abstraction. You could implement a queue. You can implement locks. But if you're happy to run a lockless systems, and there are many databases out here that kind of do this without giving up the database server, right? If you're happy to implement a lockless system, then you can do a lot with performance and flexibility, and efficiency of running a database without servers. So actually, this is not really a new idea. So there was a 2008 paper on building a database on S3, and the AWS S3 came out in 2006. So just a couple of years after, and people are already excited by the technology. And here he looks at how, sorry, he or she, I don't know the author, looks at how how you could implement databases on S3 and what you would have to give up, given the constraints of you being reasonably efficient. And you can see the diagram on the left is basically offering up the chance to run it without service, because although there's a line between the client and the database logic, the record manager and the page manager, that line can go away. So you could run all the database logic in the client. And the conclusion is that it's shown atomicity and all client-side consistency levels can be achieved, whereas isolation and strict consistency cannot. So I think I've talked about the isolation. But what they mean by strict consistency here is that writes follow reads. So it's this same challenge of having having your write be due to the data you just read. So in SQL language, just to be select for update. So you're locking the read until you've updated. And so that level of strict consistency is a challenge to do performantly. But the one that's really just below that, which is that writes follow reads, which is that if you've done a write and that write is complete, that everyone gets the data at that point, is possible in AWS S3 and many S3 implementations, and lets you do a lot. So a little bit on this is not really rocket science once you're happy to kind of take this approach. And it's stuff that we probably all know about a little bit, but a little bit about how this is achieved in ArcticDB with its data structures. So if we're going to respect the atomicity and consistency, and by the way, just delegate durability to the storage, not even worry about that, just use good storage technologies, then we need a data structure that's going to support that. So ideally, like an immutable data structure where you just add versions rather than modifying previous versions. So user 1 is reading version 5, and then you're making an update. So actually what you need to do is create a new version of the data. And then you need to reference, so you've got some symbolic link here. I'm pretending that you've got a piece of data called Apple, and you're symbolically linking that to the new version as an atomic operation after you've completely written version 6. And then any new users are getting version 6. So you can start to build database semantics on top of this, and beyond having a reference name for things and a versioning structure, you're going to have some indexes in your database, you're going to have some data. So I'll come to that in a second. So really, I've said this a number of times, but no database servers. They're all gone, no job queues, and everyone can operate independently on your storage system, but that's shared storage. So it could be a shared file system, could it be S3, and people are able, therefore, to work together as long as they figure out how to update data frames together, individual data frames. But typically, there's an ownership here because there's millions of data frames in thousands of libraries. What does this mean for your concerns in your database? I think this is an important point because it's really not just about isolation, but it's about where you'll put your concerns. Well, the things you care about, where do they sit? So traditionally, APIs, normally quite a light API, because a lot of the work's happening on your database server. The security is definitely happening there. Executing your queries, managing your transactions, building your indexes, updating your indexes is a lot of the work. And then you've got a split responsibility on the capacity, both performance and just how much data you've got between the servers and the storage, and the resiliency. The durability is kind of split across both. You don't have any single point of failure in a modern distributed system. So what happens when you make this truly serverless? Well, you're kind of giving up a little bit on transactions, but just with that kind of isolation concern. Suddenly you do have a heavier weight client, and that client is it's like the API is simple, but it's doing a lot, and that's actually doing the indexing and the execution of your queries, and then the security and capacity, resiliency are all delegated to your storage. So if you're using a world-class storage system like many of the S3 ones, you've got incredibly featured capacity, scalability possibilities and security possibilities, and incredible resiliency. And that stuff just kind of works. And then you don't have to worry about these database servers. And then the other kind of nice feature, which you might think is a bad feature, but I think it's actually a good feature at an organizational level, is that the work you're doing at your database scales with your clients. Now, if this is a web server, that would seem like a terrible idea. Okay, so I've got, I'm doing all my work in my web browser. But if I'm trying to do data science, then the reality is the users doing the most work are running on the biggest machines, and they can afford the most database work as well. So you're actually naturally scaling your workload with your users' workload, which is not just about reading and writing data, but the science in the middle. And you've got your AWS caring about everything else. So, sorry, AWS, S3. There are other cloud providers available. Right. So Another way to look at the benefits is that you end up with something, because you're not running up these servers, and yes, serverless, not having to care about your servers in the normal meaning of serverless is probably a good trend. But not having them seems like an even better option. So just have somewhere to store your data. So in this case, my example, AWS S3, make an S3 bucket. And then configure your credentials, install ArcticDB as your parsing client. So it's incredibly simple to set up like almost infinitely scalable database, and then connect to it. That's much the same as you might connect to any database, just a slightly different API. But then you've got database semantics on top of that. You're reading and writing and updating and deleting data from data frames. And a win on the back of this is that because you're using these kind of like immutable data structures, I mean, I'm allowing for deletes, but even deletes create new versions. So even though you based your design on immutability, you've got the ability to change things, and you've also got the ability to rewind time, because all those old versions still exist normally. So you get this kind of nice feature that actually ends up being really critical for data science as well, because you need to go back to different models I ran. You need to look at how the data changed, or you need to look at how your outputs changed and how that related to the model you were running to do good science. So this ends up being like a necessary and nice output of this architecture. So really just to sort of summarize, you've got this kind of like, for all the reasons discussed, we kind of ended up with this kind of fully client-side database machine that does all the work of deduplicating data, compressing, tiling, indexing, working with the storage system to create a kind of fully featured shared database infrastructure on what could be, shared file systems, cloud storage, or it could be very performant flash drives in your local data center, which is the kind of way we run it. And then, I said there was more to the data structures, but obviously you're building the indexes and you're compressing what might be tick data, what might be alternative data into columnar storage in your data layer, and you're chunking it. And in this way, you can use the indexes to pull back the bits you want. See how we're doing on time. Or I'm out of time, basically, am I? Okay. I'm going to skip that. I'll do a quick demo. I'm a passionate believer that demos explain things better than almost anything else that you can do. But it would only explain the API. So I'll do a quick demo, if I'm allowed. And then I've got a little summary I might have time for. Okay, so I'm actually VPN'd into the corporate infrastructure here. So I'm just going to do some imports. And then explain a few terms. So we have the idea of a namespace, really, oh, you can't even see it. You have to end the presentation. Okay. No one told me. Right, okay. Okay. Okay, so it's the idea of the namespaces, the bucket level in S3 parlance. So you've made some storage bucket that you've got permissions for. And then there's the data set level we call libraries. So you might put your US equity data in one and your European equity data in another, or your weather data in another. And then you've got lots of data frames in there. It could be millions for all the things you individually care about. And each of those items is a data frame. And so connect to the research cluster here. So 30,000 libraries in the research cluster. So there's a separate production cluster where we run our stuff in real life for trading. And then I'm going to just get out toy examples to show you how things work. So I'm getting a library, and I'm going to read from one library and write to another. So there's a source library and a library. And I'm listing the symbols. So these are the data frames in the library. There's just 4. So it's tiny examples, just so you can see sort of what's happening. So basically, you read and write data frames. So I'll read Amazon 1. There it is, and I'll write Amazon, and I'm added in a bit of metadata just so I can keep track of things. but you've got some database functionality. So it's not just a document store. You can append data. So let's do that. And I've made my data frame a bit longer. So I've read a piece there, and I've appended it to Amazon. And there's the slightly longer data frame. You can update the middle, and it'll be updating the indexing and the versions for all of this. And in fact, you might have seen, yeah, here you go. When I did the original write, you can see that I've run this demo a few times, version 625. So here I'll do an update in the middle of the data, and you can see, if you've been watching very carefully and very quickly, you can see the middle of the data's changed. So also the time travel, so all of these things are new versions. So I can get the last version, but then I can go back to a version number, or I can put in a timestamp and just find the version at a time. So that was the original version. But all these are toy examples. So this is running in a Jupyter Hub notebook. It's 2 virtual cores, so it's actually very small. I'm not doing myself any favors by running on a tiny VM. But I'm going to get an example with lots and lots of floats in, 100,000 columns, 100,000 rows. I'm just going to pluck out 3 columns and a few months of data. And I'll see that's the tail of the data frame there. And then it works with tick data is a clear use case. So here, this is actually Bloomberg data. So level 1, that means like bid and ask data from Bloomberg. So that our level 1 data set there for equities has 66,000 equities. So pull out some columns, just 1 day of data. So it took about 1/3 of a second, 1.3 million rows. Just to prove the data came back. It's not very interesting data, I'm afraid. And then there's GUI functionality. So this is the classic New York taxi data set for yellow cabs. And here I'm trying to find out who are the really heavy hitters. So this is like pandas style query functionality. So where are people tipped so much that it's 95% of the total amount? Like they've tipped $100 on a $5 fare. And there are those. People do that. So there you go. So it fills and works like pandas, which is the kind of skills that people have learned in Python to work with data. So that just to give you a little bit of a feel for how ArcticDB works in practice for users. And then I will try and get back to the 3 minutes, perfect. Well, what I will do is just summarize them, because I have another story about trying to create a business inside a large corporation. But I will just summarize instead, so there's a few minutes for questions. So this is used in anger. So here, running 40 gigabytes per second out of these flash storage on the right, no database servers, straight to Python users. Typically, they're running clusters of machines to do their calculations. And that is, so if you're using a fast networking of like 40 gigabit like networking, then that's like over 10 of those, right? So you're using a lot of networking to do this. And this is just like every day. This is multiple days sustained. So it's like billions of rows per second. So it works. Quick shout out to Detail, which is like a nice pandas visualizer, and actually our most popular open source tool, if you want to check that out. But I should mention that we're not doing this alone. Bloomberg have been helping us with this. They're a user of it in bquant, which is their quant data science Python tool they sell, which has like data already in it, so it's quite cool. And QuantStack, which are a French company that you may know, who've done a lot of work on Jupyter and Conda Forge, Mamba, Micro Mamba, things like this. They're a pretty cool open source focused company. And so with their help, we're building this out. And I hope as many of you as possible find that interesting and usable. There's a much longer disclaimer, which you can ask me about if you want to read. But really, it's about the QR codes, feedback on the left, and check out ArcticDB on the right. What I noticed was your phone might only show one QR code, so I will know which one you're choosing by which way you point your phone to mask out the other one. So if you want to get that one, you need to make sure that one's out of the image. So anyway, please provide feedback or check out ArcticDB. And with that, hopefully there's time for questions. Thank you.
Thank you very much for the talk. Quick question. Under the hood, what's the optimization happening on the pandas data frames, which we obviously know are not very good at scaling up to billions of rows? Like, how are you kind of doing that?
Sorry, what, under the hood, what?
On the pandas data frames, what kind of optimizations are you running under the hood? Like, are you doing some kind of a Spark-based?
So the general pattern we have internally is that and the users have, is that you're returning pandas data frames that are usable. So they're fitting in memory. But you're doing the querying to like limit your results to that. But then once people have got their data frame back, they might choose like another technology like Polar's DuckDB to do their analytics, depending on if they don't like pandas or they think it's too slow.
Distributed, or they are kind of stored in a single node of the cluster, or they're kind of distributed across?
So they're distributed across the storage, which is your sort of storage provider's problem, and something they're actually pretty good at solving.
Okay.
Yeah. And generally, like actually AWS will dynamically like distribute your data to make sure it's like meeting demand.
Okay.